All right, let's go ahead and wrap this chapter up, talk about dependent sample means. Now, in this case, we're talking about dependent samples. So this, when you're doing problems with this, you're usually talking about like a before or, a before and after type study. Before and after. Like, rate your pain after study? Rate your headache pain after taking an aspirin. So they would take 20 people, so n equals 20, and they would end up with x1, x2. These are the ratings of the data all the way up to x20, and this would be before, right? And then they take the ratings afterwards, x1, x2, x3, down to x20, and this is my after score. And then what I do is I take the difference. Then I take the difference. And this would be x1 before minus x1 after, etc. Yeah, I know that notation looks awful because it looks like they're all going to be zeros, right? So before and after studies work really, really well with this. But there's lots of other applications. We're actually going to do one for your example today. I think you'll enjoy it, all right? But what we're talking about is a dependent situation. All right. Now let's talk just like always. Oh, by the way, these are great medical studies. Medical studies work really, really well with these because if you think about it, you take a sample, and what you want to do is you want to match them. This is called a matched pairs design. This is also called, whoops, I'm supposed to be in there. This is also a matched pair because the person who's got the headache is matched to themselves. So you've got some patients that are over here, and they're going to have an average, and then you're going to have some patients that are over here, and they're going to have an average. But what we want to do is we want to match as all of the people in here with all of the people in here. So if they're 170 pounds and they're Hispanic and they're male in the placebo group, you know, the placebo group is the group that receives no treatment, and they're 100. We want to have a 170-pound Hispanic male over here. Okay, that's really hard to do in medical studies, and I think they fudge it a lot, but you need to understand that that's another really good use for them. All right, now let's talk about our assumptions. As always, assumptions are key in all stats because you have to make sure that you meet them. Okay, so number one, first and foremost, samples are dependent. In other words, they can be matched up somehow. Dependent. And this word can be really tricky. They have to be dependent in the same way. In other words, that dependence can't vary. And we'll get into that more in class, but it's consistent, like a before and after. We're dependent, in other words, the data value from person number one when they measured his or her pain, and it's still person number one. And that's true throughout. All right, so that dependence somehow doesn't change throughout, and that can get a little muddled sometimes. Of course, your samples are SRSs, so simple random samples, and then either or both. So just like always, we either want the number of people. Now think of these not as, like, maybe I didn't draw this in the best way because this might imply that I've got different size groups, like this has an N1 and this has an N2. No. Since they're matched, since they're dependent, we're going to have just an n. All right? So in this case, the number of paired values in our dependent sample, we want n to be greater than 30. We know the sample comes from a normal distribution. Sample comes from a normal distribution. Boy, that normality is a big, big assumption, isn't it? It's called the normality assumption from normal distribution. So from normality, fine. Let's leave it right there. Okay? All right. Now, I'm going to give you the test value, okay? And we'll just look at it here for just a sec because it might strike you as being a little bit strange. It's going to be t because what we're going to end up with is we're going to end up with, well, I'll show you. I'm going to use d bar minus mu sub d, and we're going to divide this sucker by the standard deviation of d divided by root n. All right, this probably looks pretty familiar. All right, remember when we first got introduced, it was x bar minus mu over s divided by root n. Remember that? But in this case, look at this. What this D bar is going to be, D bar is just going to be the mean of the differences, the before and after, the patient 1 with patient 2. Mu D is going to come from, what we're going to have is we're going to have a null hypothesis and an alternative hypothesis, and it's going to be mu sub D equals a number or it equals 0, and then mu sub D. This is basically the average of this is the parameter average or parameter mean of the differences. And this could be equal, 0, greater than 0, less than 0, or it can be any other number, okay? Just like we've talked about in the past. So this is the parameter. Wow, a little too much caffeine. Sorry, guys. This is the parameter mean of the differences, and it's often 0. Okay, this S sub D is the sample or the statistic standard deviation of differences, of diffs, and then n equals number of pairs. Number of pairs. And just like before, number of pairs. That's why we can often claim dependence when we pair stuff up. Okay? And just like before, where should I put this? I'm going to put this sucker in red. We're going to do, let's do degrees of freedom is just n minus 1. Just like always. Sorry about my work right there, you guys. Okay? All right, cool. Now, I'm going to go ahead and I'm going to give you a problem. I'll leave it in red. I think you'll like this. I want you to try it out. I want you to give it a shot, see if you can figure out what exactly is going on in this thing. So on page 483, I want you to try number 15. It's kind of a compelling problem, and we'll discuss it. But I want you to think about things like the assumptions. Really go kind of delve into the assumptions and make sure that there's at least an argument for why we can do what we can do, why we're allowed to do this paired samples or dependent samples test. Okay? So enjoy, and I'll meet you back with the problem keyed out, and we'll have some fun. All right, let's go ahead and knock this one out. All right, first and foremost, if you look at the problem, let's make sure that we have dependent samples. Let's make sure that we meet all of these assumptions. All right, and I realize that we're going to have to do a little bit of this on faith, so bear with me. Why are they dependent samples? Well, the data comes from the same hospital. All right, so think of it as a hospital a week before Friday the 13th, and the same hospital the week of Friday the 13th, or the Friday of. So think of it as the Friday of. Does that make sense? The other thing, there's no assumption. It doesn't write anything that we know that this is being drawn from an approximately normal distribution. But seeing as how n is only 6, we have to assume that that's what's happening. We didn't write the problem. We didn't come up with the study. So we have to assume that we're drawing from a normal distribution. Okay? Now let me show you what I do here. Is I simply write a list of the differences because I need the mean of the differences. So I wrote all I did was subtract the Friday the 13th from the week before. And for the first data value, I got 4, I got 6, I got 3, I got -1, I got +1, and I got 7. I found the mean, which was 3.33. I threw this in my calculator. I didn't do this by hand. I got 3.01. Now, I realized that when I was lecturing at you before, I guess I'm not lecturing per se, I never mentioned the confidence interval. But stumble back here and look at your confidence interval. It's easy to build from the t-value. For a 95% confidence interval in this case, or for any confidence interval, it's simply, we know that the average, the parameter for the difference is going to be d bar minus the error and d bar plus the error as far as what goes on the endpoints of the interval, and the error is just t sub alpha halves times the standard deviation of the differences divided by the square root of n. All right, so if we get back to this problem, check it out. I know that the degrees of freedom are 5. I know that I've got a two-tailed situation going on over here, plus we're going to do a confidence interval anyway, and that's why we're allowed to do that, because it's two-tailed. And then I just used my formula. I took 3.33, I added 2.571. Where did I get this? I went to degrees of freedom of 5. I went to my chart, which was the area in both tails is 0.05, 0.025 over here, 0.025 over here. You add them up, both tails, you end up with 0.05. Throw it in my formula, and I end up with 0.171 is less than the mean of the differences, which is less than 6.489. Well, clearly, 0 is not in there. So what do? We throw it out. We reject it. And then our quick little write-up is, since the mean of the differences, which equals 0, which was the null hypothesis, doesn't lie in the 95% confidence interval around the mean of the differences, there's evidence that the occurrence of hospital admissions is affected by the date, or by Friday the 13th. We'll get better at writing these up. Now, I went ahead and said, okay, let's do this anyway. Let's go OR, and let's throw it in here. Because if you notice, wait, let me back up before I get too jiggy with it. You notice 0.171 is just a little touch bigger, right? It's like 0.17 of above 0. Now let's see if that plays out the same way. If I throw it in my t value, I got t equals 3.33 minus, remember this guy is mu sub d, which I steal from my null hypothesis, minus mu sub d divided by 3.01 divided by root 6, and I end up with 2.709. All right, so 2.709, let's see where that ends up. 2.709, yeah, that just barely ends up right here, doesn't it? However, it's significantly different. Think about it this way. The p-value, or the probability that this occurrence would happen because of chance, is significantly small enough that there is evidence that we can throw out the null hypothesis and assume that hospital admissions are affected by the date. Hey, hope you enjoyed it. Don't worry about trying to memorize formulas, but by God, you better be able to use the formulas, all right? So don't just back down off of all the homework and say, I can use my formula sheet and I'll be fine. There's a boatload of formulas with the assumptions. I think the most important thing that you understand is you make sure that you understand the assumptions, okay? I'm not going to lie to you. I don't memorize these formulas other than like the Z. That's not true. I memorize most of the formulas, okay? But the thing that's most important for me is that I memorize the assumptions, that I remember, okay, wait, do I know sigma or do I just have S? Where do I use T? Where do I use Z and Y? All right, and again, we're going to write all this up, put them on posters around the room so you don't have to memorize them. You just got to make sure you use the right one. Know how to use your charts, know how to use your calculator, etc., etc. All right, I hope you enjoyed Chapter 9, and we'll see you in Chapter 10.